Hello everyone, welcome again. In first part we have discussed about combination of lenses and the prism formula. So this is the prism formula, angle of incidence plus angle of emergence. It is given by angle A plus angle of deviation. So this formula it is called as the prism formula, and this is nothing but the relationship between angle of incidence, angle of emergence, angle of prism and angle of deviation for the light ray produced by this prism, right? So it says that for the given angle of incidence there is some angle of deviation. That means if angle of incidence changes, angle of deviation also changes. Now we will produce a formula to find out the refractive index of the material of the prism. For that, let us proceed. So from the prism angle we already know that prism angle and the prism formula we already know that at this angle of deviation, it changes with angle of incidence. As the angle of incidence changes, its value also changes. So when we plot the graph between angle of incidence and the angle of deviation, by taking deviation, angle of deviation along the vertical and angle of incidence along the horizontal, we get a graph just like this, right? So we are looking at that as the angle of incidence increases, angle of deviation goes on decreasing till there comes one particular value of angle of incidence where angle of deviation becomes minimum. There is no minimum value for the angle of deviation than this. There is no lower value for angle of deviation than the minimum angle, which is for a particular angle of incidence. If we still increase the angle of incidence, we see that angle of deviation no more decrease, but it starts increasing again, right? So we get a graph just like this. So that means there is one particular value of angle of incidence for which the angle of deviation is minimum. What happens here is very interesting. It happens that in that particular situation, when we get a minimum angle of deviation, which is for particular value of angle of incidence, at that particular angle of incidence, this angle of incidence, it is always equal to angle of emergence. So in that particular condition or situation, angle of emergence becomes equal to angle of incidence. And also this refracted light ray PQ, it becomes parallel to the base BC of the prism. Due to that, an important result come into conclusion that R1 and R2 both are same. So let me just sum up once again. When we get angle of deviation to be minimum for particular value of angle of incidence, at that value of angle of incidence, angle of emergence, it is equal to angle of incidence. The refracted light ray, it is parallel to the base. PQ is parallel to BC. BC is the base, PQ is the refracted light ray. And these angles R1 and R2 together from here, these two together are equal. They become equal. So now we can make use of this condition in order to write the formula for the refractive index of the material of the prism. Now we get already know that this angle A, it is equal to R1 plus R2, and because R1 and R2 in this particular condition of angle of minimum deviation are equal, so they become 2R. So if we represent R1 and R2 both by R, then it simply gives 2R. So that R means angle of refraction becomes equal to A by 2. We are taking 2 to the other side to divide A. And also from this prism formula, it is I plus E, both are equal. So we are using I in place of E here, and it is A plus delta. Delta, it is nothing but the minimum angle of deviation, right? So we write it as delta M. From here we write I, the angle of incidence, which is 2I because I and E both are equal. So I becomes equal to A plus delta M divided by 2. Now we get angle of refraction, angle of incidence. Now we can write the Snell's law for the refraction happening here whenever light ray passes through a prism. So it is called as a sine of angle of incidence divided by sine of angle of refraction, which is R1, which is R, because both R1 and R2 are same. So in this, when refraction is happening, so Snell's law says that sine of angle of incidence divided by sine of angle of refraction, which is R1 or simply R in particular condition, this will be equal to refractive index of material of the prism to the refractive index of the air. So it is simply mu. So it is the refractive index of that material of the prism, because the refractive index of air is 1. So now we substitute the value of I and R from here and here. So we get refractive index of the material of prism to be sine of angle, this angle of incidence, which is A plus delta m by 2, divided by sine of angle of refraction R, which is A by 2. So this is the formula with which we can find out the refractive index of the material of the prism. Not just this, if we have a hollow glass prism, then we can fill any transparent liquid, just like water, kerosene oil, glycerin, or any other transparent liquid, for example vegetable oil, and find, with the same method we can find out the refractive index of those liquids by using the same formula. So this is the formula for the refractive index of the material of the prism. Let us proceed further. Now we take a special case. What if the prism is thin and also angle of incidence is small? So these are the two conditions which we are going to apply here and see, check what result we get here. So we take that the angle of prism, this angle is very small. So which is the case of a thin, we can say prism. So when prism is thin, this angle becomes very small, and in that case, whenever we keep the angle of incidence small, this angle of incidence is small, right? In that case, we will come to know about a very important result. So let us proceed. So whenever this thing happens, then we can write the formula for the Snell's law for the refraction happening at face AB and at face AC. So for first phase AB, the Snell's law, it is given by mu, which is equal to mu I upon R1, sine of angle of incidence divided by sine of angle of refraction R1. And similarly, the Snell's law for phase AC, it is refractive index of air divided by refractive index of glass, because now the second medium is air, which is equal to sine of angle of emergence, means refraction, this is here, divided by sine of angle of incidence, which is R2 here. So there will be one difference, that in this case the light ray is coming from air to glass, and whenever refraction happens at this surface, the light ray is going from denser to rarer medium, right? So this is the angle of incidence here, and this is angle of refraction. So angle of emergence will be the angle of refraction here. But if we already know the about refractive index of that, the refractive index of medium 1 with respect to other, it refractive index of medium 1 with respect to 2, it is equal to the reciprocal of the refractive index of medium 2 with respect to the 1. So we can just take the reciprocal of it, and we get again the refractive index of glass with respect to air, which is simply mu as earlier one. So it becomes sine E. Here sine E is the angle of emergence which act as this angle of refraction here, right? So it is E here. In place of I2, you take it as E, the angle of emergence, divided by sine of angle of incidence, which is R2 here. Okay. Now for these conditions of thin prism, for small angled prism, and also for the small angle of incidence, what happens? These angles become equal to their sines. So sine I is very nearly equal to I, sine R1 it is very nearly equal to R1, and similarly sine E it is very nearly equal to E, and sine R2 it is very nearly equal to R2, because angles remain quite small. So in that particular case, this equation becomes mu is equal to I upon R1, and this equation becomes equal to mu is equal to E upon R2. Now here, from here we find I becomes equal to mu R1, from here we find E. E becomes equal to mu into R2, and we add I and E together. So I plus E, it will be equal to mu R1 plus mu R2. Taking mu common, inside we have R1 plus R2. We already know that the sum of these two angles R1 and R2, this is nothing but equal to angle of prism, right? Again, according to this relation. So we get that I plus E, it is equal to mu into A. Now we can apply the Prism formula and substitute the value of I plus E from here. So Prism formula says that I plus E is equal to A plus delta. Now I plus E, we have in this particular conditional situation, we get it to be mu into A. So I plus E becomes equal to mu into A. So A plus delta becomes equal to mu into A. And from here, delta, the angle of deviation, can be written as, it is A goes to the other side and it becomes A into mu minus 1. So this relationship holds if the prism angle is very small and also angle of incidence is kept very small. Or we can say light ray is incident at a very small angle of incidence. In that case, we see that the angle of deviation is independent of angle of incidence. In that case, the how much deviation will be there, it will not depend upon the angle of incidence of the incident ray. Let us proceed further. Next phenomena which is interesting to know, it is the dispersion of the light. So whenever we have a light which is composed of two or more than two colors or lights, then the light, it is called as the composite light or compound light, right? So whenever such a compound light is passed through a prism, its dispersion takes place. So what dispersion means here? For this, in place of composite light, we are taking as the white light, the light which comes from a bulb or tube light, or the light which comes from the sun. All these lights are the white light. White light, it is nothing but it is the combination of the 7 color lights, right? So it is the combination of 7 colors of the lights. That means the white light contains 7 kind of colors, but because they travel along the same path, right, along the same line, so they give the appearance of a white light. So whenever such a white light, it is allowed to pass through a prism, just as we have discussed. So whenever a beam of light or a ray of light, white light, it is passed through a prism, its refraction happen, and due to that refraction, these colors get separated from each other, or we can say gets split into its constituent color. White light gets split into its constituent colors. This splitting of the light into its constituent colors, it is called as the dispersion of the light. So the phenomena of separation of the constituent colors, whenever light pass through a composite light pass through a prism, the phenomena is called as the dispersion of the light. So here our task is to understand why this separation of the light takes place whenever light ray passes through a prism. The reason for this lies in the refractive index of the prism for the different colors. The refractive index of the material of the prism or for any transparent medium is different for different colors of the light, or we can say colors means wavelengths. For different wavelengths of the light, the transparent mediums have different refractive indices. There is a criteria called as Cauchy's criteria, who says that the medium will have a higher refractive index for the color having the least wavelength, and the medium will have least refractive index for the color having the highest wavelength, or we can say longest wavelength. When we talk about the white light, it has 7 colors, out of which 7 colors are remembered as Vivgyor, out of which this red color has the highest wavelength and wavelength goes on decreasing, and violet color has the least wavelength of all the 7 colors. That means the refractive index, according to that Cauchy criteria, the refractive index of this material of the prism will be least for the red color, because the wavelength of the red color is highest, right? So we can say that the refractive index for the red color will be least, and the refractive index will go on increasing as the wavelength goes on decreasing, and for the violet color, for which the wavelength is least, the refractive index will be highest. Or we can say the value of the refractive index of the material of the prism will be largest for the least wavelength of the violet color of the light. Now if you focus again on this formula, then it says that deviation will be more for higher refractive index and deviation will be less for the less value of refractive index. That means if the refractive index of the material is less, then the deviation will be less, and if refractive index of the material is more, then the deviation will be more. Now we can apply this here because red color has the least refractive index of the prism. So therefore the deviation in the red color will be least of all the 7 colors. And as for the violet color, the refractive index is highest, so therefore the violet color will suffer highest deviation. Angle of deviation for the violet color, delta V, it will be highest. So the 7 colors, different 7 colors will suffer deviation along different angles at different angles due to their due to the different refractive index of the prism for these different colors due to their wavelengths, right? So the red color, which has the highest wavelength, has the least refractive index, and therefore it will have the least deviation, and the deviation will go on increasing because wavelength go on increasing, due to which the decreasing, the wavelength go on decreasing, and the refractive index goes on increasing. So with the increase in refractive index, this according to this formula, the deviation will be increasing. So therefore violet color bends largest and red color bends least whenever it passes through a prism along the path of the white light. So this is the reason why the dispersion of the white light or any composite light takes place whenever it passes through a prism. So the reason lies in Cauchy's criteria, which simply says that the light which has the highest wavelength will have the least refractive index of the medium and hence will suffer the least deviation. On the other hand, whenever the wavelength of the light is large, its refractive index, least. Whenever the wavelength is least of the light, the refractive index of the material of the prism will be large, and therefore the angle of deviation will be large for that particular color. Okay, so now we will learn about two important terms here. One is angular dispersion. So what is angular dispersion? So this is the quantity which is defined for two colors which are passing through the same prism. So what is angular dispersion? So this is a prism here, as you can see in this diagram, and we are using a beam of white light which is composed of violet and red color. Suppose that violet and red color are allowed through the prism, then they will suffer different deviation by different angles depending upon their wavelengths. The higher one will suffer least, color of higher wavelength will suffer least deviation, and the color of least wavelength will suffer highest deviation. So here we are taking the two colors, for example red and violet. So red, the angle of deviation for red is represented as delta R, and for the violet color it is represented as delta V. Initially all the colors are coming along the same direction, right? So angular dispersion, it is nothing but it is the difference in the deviations suffered by the two colors while passing through a prism. So whenever two colors are passing through a prism, how much deviation they suffer, the difference of their deviation, difference in the deviation suffered by these two colors, it is called as the angular dispersion. So this delta V minus delta R, this will be equal to angular dispersion. It will be written by theta. So angular dispersion for violet and red color of rays, for example, there can be any other colors. It is given by theta. It is equal to delta V, the deviation in violet color, minus deviation delta R, deviation in the red color. So this relationship, or this is the formula for angular dispersion, or this is how we write the angular dispersion. Here delta V according to this formula, we can write delta V and delta R. So delta V, it will be equal to A into mu V minus 1. Mu V, it is nothing but the refractive index of the prism for violet color. And similarly, we can write delta R, which is equal to A into mu R minus 1. Mu R is the refractive index of the same prism for the red color, where A, angle of prism, is same. So whenever we substitute these two values here, we can calculate the angular dispersion, so that it becomes A into mu V minus mu R. So this is the formula for the angular dispersion. Another important term which is interesting to know here, it is called as dispersive power. Dispersive power is the power of the prism for dispersion in the colors of the light. So how do we define dispersive power? A dispersive power of a prism for the two colors, it is nothing but the ratio of angular dispersion for these two colors, right? Ratio of angular dispersion for these two colors to the deviations suffered by the mean light. Mean light is the one which has the refractive index between the given two colors. Suppose that we have a white light which is composed of 7 colors, right? So mean light here, it is called as yellow color of light, because for yellow color of light, the refractive index lies exactly between the refractive index for the red and the refractive index for the violet color light. So yellow, it is called as the mean color of the light. So dispersive power, it is nothing but angular dispersion. Angular dispersion is nothing but what we have discussed here. So it is the ratio of angular dispersion for the two colors to the deviations suffered by the mean light of the two lights, right? So it is called as delta. So this is dispersive power. So we represent it by omega, which is equal to delta V minus delta R, means theta, angular dispersion, divided by delta, the deviation which is suffered by the mean light. So if for example mu is the refractive index of the material of the prism for that mean light, then deviation in mean light, it can be written as delta is equal to A into mu minus 1, which is the same expression as we have discussed earlier here, right? So whenever we use all these notations and substitute here, we get the dispersive power of the prism for these two colors of the light, for example red and violet. If we take red and violet, then their main color of light will be yellow color light, for which the refractive index is mu and deviation is given by this. So whenever we substitute the values, so it is delta V minus delta R, which is A into mu V minus mu R, right? So this angular dispersion, it is given by this, divided by delta is equal to deviation in the mean light, which is given by A into mu minus 1. So A into mu minus 1. So A cancels out, and what is left, it is called as the dispersive power. So this is all about the prisms and the terms related with the prism, just like the angular dispersion and the dispersive power. That's all. Thank you.